Modern GPS navigation gives pilots their exact coordinates on a moving map. You look at a screen and you know precisely where you are. Before satellites, pilots relied on a system that provided only a fraction of that data, forcing them to solve their absolute position using manual geometry. That system centers on the Automatic Direction Finder, or ADF. The dial is aviation's mechanically simplest navigational instrument, requiring the pilot to perform all spatial calculations without automated assistance. The system requires a ground-based transmitter known as a non-directional beacon, or NDB. These are physical antenna masts anchored in fields near airports or airways. They transmit on the low-frequency to medium-frequency bands, typically operating between 190 and 1750 kHz. The defining physical characteristic of an NDB is its omnidirectional output. The mast radiates identical electromagnetic energy outward in 360 degrees simultaneously. When an aircraft intercepts these radio waves, the onboard receiver detects exactly one variable: the direction the wave came from. This single data point creates a strict navigational limit. The radio wave identifies the direction to the tower, but it provides zero absolute data about where the aircraft is located on a map. While it is tempting to simply put the needle on the nose and fly toward the beacon, relying on the pointer alone without a geometric plan can lead to significant course deviations. To navigate safely, an instrument pilot must master the mental geometry required to fuse these relative radio signals with the aircraft's absolute magnetic heading. Without this mathematical translation, the cockpit's simplest backup navigation tool can quickly become a source of geographic disorientation. The process begins at the ADF receiver on the radio panel. Unlike modern digital instruments, the ADF has no failure flag. If a signal drops or the station goes offline, no red warning appears on the display. This hardware limitation dictates a mandatory verification workflow: selected, identified, and ADFing. Pilots find the necessary data in the airport/facility directory. For the Burnett NDB, the pilot first dials the frequency 341 into the receiver. Directly next to the frequency is the Morse code identifier, BMQ, which identifies the specific transmitter. To confirm the station, the pilot switches the mode selector to ANT, or antenna. This mode provides the clearest audio reception for Morse code identification, but removes all directional data from the needle. For stations transmitting unmodulated carrier waves, the pilot uses the BFO, or beat frequency oscillator. This imposes an audible tone over the wave, so the Morse code can be heard. Once the station is matched to the chart, the pilot must move the selector back to the ADF position to reactivate the directional needle. Leaving the switch in ANT mode is a common error. The needle will remain stationary, offering no visual cue that it is no longer tracking the ground station. If the NDB is the sole aid for an instrument approach, the pilot must monitor that Morse code identifier continuously until the aircraft is on the ground. Because these radio waves are invisible and fail without warning, that repetitive sequence of beeps is the pilot's only way to confirm they are receiving a valid signal. The primary display for this information is the fixed card ADF, also called the Relative Bearing Indicator, or RBI. On this dial, the card is stationary. The top of the display, marked 000, is fixed to represent the nose of the aircraft at all times. Because 000 is always the nose, the numbers on this specific card have no direct relationship to magnetic north. The needle indicates the relative bearing, the angle measured clockwise between the aircraft's nose and the direction of the NDB. If the NDB is sitting directly off the right wing, the needle will point to a relative bearing of 090. If the pilot turns the aircraft 90 degrees to the left, the station's physical position on the ground remains the same, but because the nose has changed direction, the relative bearing changes with it. The needle swings to 180, indicating the station is now directly behind the aircraft. Crosswinds add another layer of complexity. To stay on a straight path over the ground, a pilot must angle the nose into the wind, which shifts the relative bearing of the station. This is why homing, constantly turning the nose to keep the needle at 000, fails. In a crosswind, homing results in a curved, inefficient flight path that drifts further downwind with every correction. The RBI needle accurately shows where the station is compared to the aircraft's longitudinal axis, but it cannot define the aircraft's absolute position on the map. To solve the geometry of orientation, the pilot must reference a second instrument, the heading indicator. The heading indicator provides the missing absolute value needed for the calculation, the aircraft's magnetic heading. Because this instrument relies on a gyroscope, it suffers from drift, up to 3 degrees every 15 minutes. The pilot must manually realign it with the magnetic compass during steady flight to maintain accurate data. With an accurate heading, the pilot applies the primary NDB equation. Magnetic heading plus relative bearing equals the magnetic bearing to the station. Pilots often visualize this by paralleling the needle. By mentally superimposing the angle of the ADF needle onto the heading indicator, the absolute bearing becomes clear. For example, if the heading indicator shows the aircraft is on a magnetic heading of 280 degrees, and the ADF needle shows a relative bearing of 030 degrees off the nose, adding 280 and 030 identifies the absolute magnetic bearing to the station as 310 degrees. Without this calculation, flying away from a station is nearly impossible to do accurately. The needle simply points behind you, providing no data on which of the 360 possible tracks you are actually following. This equation is the only way to convert a relative radio signal into a definitive, navigable line on an aeronautical chart. These theoretical calculations are put to the test during an actual instrument approach, where a pilot must track a specific bearing to the runway through clouds. The anchor for this approach is the CLIFS Locator Otter Marker. CLIFS is a compass locator, a low-powered NDB with a restricted range of about 15 nautical miles, used specifically for local maneuvering and final approach segments. Executing this approach accurately requires managing the environmental interference inherent to the low and medium frequency radio bands. Thunderstorm effect is a significant source of signal distortion. The electromagnetic energy from lightning can overpower the beacon's signal, causing the ADF needle to point toward the storm instead of the station. Pilots must also watch for night effect. At dawn and dusk, the ionosphere refracts radio waves back to Earth as sky waves, which can cause the signal to fade or the needle to wander. Coastal and mountain effects further complicate the signal, as radio waves can physically bend when crossing shorelines at an angle or reflecting off terrain. Because of these limitations, the FAA is steadily decommissioning NDB facilities in favor of more reliable GPS and RNAV approaches. Eventually, the NDB approach will disappear from modern instrument flight entirely. While the physical towers are being phased out, the mental geometry required to use them develops a specific proficiency in spatial orientation. It requires the pilot to manually reconcile radio signals against their heading, a process that modern automated systems have largely internalized.